Welcome to another episode on this channel. Today we are going to be looking at cryptography. Now, what is cryptography? So, cryptography is the study of methods of sending messages in hidden form so that only the intended recipient can remove the disguise and read the message. Now, the messages that we want to send is called the plain text, and the hidden messages is called the cipher texts. Now, the process of converting the plain text to cipher text is what we call the encryption, and the reverse process is called the decryption. Now, let's look at what we call the Caesar cipher. So, Caesar ciphers. A Caesar cipher is a type of substitution cipher in which each letter in the plain text is replaced by a letter with some fixed number of positions down the alphabet. What do we mean by this? Now, Caesar cipher was named after Julius Caesar, who was known to have used this encryption technique to protect his messages. So now, for instance, if Kojo wants to send hello to Abena. Now, I don't want to just give, because during that time, during the time of Julius Caesar, there was nothing like a phone or something. So if, for instance, I want to send this hello to Abena and I want to give the sheet to someone to send that message, because I do not want that person to read that message, I want to now encrypt this. So we have the plain text. So the plain text is what I want to send, and that is hello. Now, I do not want to send this hello because anyone can read the message. So I want a cipher text. Now, how do I get a cipher text? Before I send the message, me sending the message and the one receiving the message, we both know the key to use. So the key, as in, we get a specific number. So for instance, using the English alphabet, we have 26 alphabets, right? So we have 25 different sets of transformations. That is, when we consider the English alphabet from A to Z. So A is 0, B is 1, C is 2, D is 3, E is 4, all up to Z, which is 25. So we have 25 different shift transformations. So for instance, if I decide to use C to be my key, so for instance, if I say that C is equal to 3, then Abena also knows that now C is 3. I am Kojo. I want to send hello to Abena. So now what I would do is I would then add 3 to each of my plain texts. So now we know that looking at this, using the English alphabet, looking at this, our H, so hello, right? So let's do it this way, hello. Our H corresponds to 7, E is 4, L is 11 again, and O is 14. Now, if I am to add 3, which is my key, to each of these letters, I'm going to get over here 7 plus 3 is 10. This is 7. This is 18. Sorry. This is 14. This is 14. And this is 17. So the 10 corresponds to letter K, 7 corresponds to H, 14 corresponds to O, another O, then 17 corresponds to R. So instead of hello, the cipher text will now be KHOOR. Now I'll write this KHOOR on a sheet of paper and send it to Abena. So if Abena gets the sheet of paper and she sees it, she now has to decrypt this message to actually know what it means. But because Abena already has the key, which is 3, she can now just subtract 3 from each of these letters. So when I am sending, I add 3. But when the person receiving the message wants to decrypt the message, he or she now subtract 3 from each of the letters. Now, if I am to subtract 3 from K, so we know K, we know H, we know O, and R, right? So K corresponds to 10, H is 7, O is 14, and R is 17. Now, if I am to subtract 3 from these letters, I'm going to get 7, 4, then 11, then 14, right? Now we know that 7 is H, E is 4, 11 is L, and this. So now the person receiving the message can now get to see that indeed you want to send hello. So it's just a form of greeting. So hello. So whatever the sender was trying to send was hello, but instead of sending the hello, he or she sent KHOOR. Because they both have the key, if the receiver wants to decrypt the message, he or she also has to subtract 3 from it, right? So that's basically what we are trying to do. So in general, our f of s is always equals to x plus c in modulus n, where for instance, in the English alphabet, our n is equals to 26. Now, if you want to decrypt this, now f inverse will be equal to x plus n minus c, or in modulo n, right? So in our case, our f of x is equal to x plus, and remember our key that we were using is 3, so plus 3, or in modulo 26. So if you have, say, hello, so h, you just, in place of x, you put in the value of h. So you're going to get, so for instance, f of h, x is now 7, so 7 plus 3, or in modulo 26, you're going to get 10, and that corresponds to k. So you're going to do the same thing. So you're going to get KHOOR. Now, if the receiver wants to decrypt, if the person wants to decrypt, now f inverse of x is x plus n minus c, or in mod n. So now f inverse will be, say, x plus, now n is 26, so 26 minus our c, which is 23, or in mode 26, and it will get, the person will now get back the hello. So now this is what we call the Caesar cipher. Now when it comes to Caesar cipher, there is one major thing that you have to look at. But before that, for instance, if I want to see if King Caesar want to send this, say plain text is there is war. Looking at this, definitely he's not going to send there is war, you understand? He has to encrypt this message. That's the encryption process. So now he will now decide the key that he wants to use. So let's say that in this case he's going to use a key of 1, meaning that he's going to add 1 to each of the plain text letters, right? So now our cipher text, if you add 1 to t corresponds to 19. So if you add 1, you're going to get 20, which corresponds to u. H corresponds to 7. If you add 1, I'm going to get I. So it will be of this form. UIF SF JT X BX. So now instead of sending the SWOR, he's going to send UIFSF JTSBS. So if he is to give this to anyone, to send it to whoever he wants to send a message to, if the person look at this, he can't read the cipher text because it doesn't make sense. So if you do not know the key, it's not going to make sense to you. But once he sends it to maybe say King Solomon or whatever, when King Solomon gets this cipher text, he also knows that they are having a conversation using a key of 1. So he's going to subtract 1 from this cipher text, and once he does that, this message is now going to make sense. He's now going to get the SWOR. You understand? So that's how this Caesar cipher test works. Now there's one major disadvantage. The disadvantage is there is a security weakness, in the sense that we have only 25 possible keys, right? We have from 0 to 25. If one tries the brute force attack as in the person, if I'm to give the message to say Edward, send this message to probably King Caesar, right? And if Edward tries to use the brute force attack where he's going to try all the possible keys, because we have just 25, if I give UIFS whatever to him, to Edward, and Edward, okay, let me try and decrypt this message. So he'll try and subtract 1, 2, 0 up to 25. And if he does that, he's indeed going to read the message, because we have 25 possible ways, and that's so simple, right? So that is the only negative aspect of this. Okay, so now let's look at this. In the English language, the most frequent letter is E, followed by T, with a probability of occurrence 0.127 and 0.09 respectively. So for instance, if I want to send a message, I have the cipher text, which is say K Q T B G W X, then G Q T T R N S, then X U W N X L, then F S I. We have Q J F A J X, then K F Q Q K W T R. We have Y W G J X N X F Z Y Z R S. Now looking at this cipher test, we now want to decrypt this to get our plain text. And now in decrypting this, over here, what you have to do is, you don't actually know the key, right? You don't know the key to this. So first of all, you have to check the frequencies of each letter. And looking at this, we have 50 letters in all. So in checking the frequency, you'll get to know that Q, G, and S all have frequency of 5. So because they have frequencies of 5, then it means probably one of them corresponds to the most frequent letter in the English alphabet, which is E. So if indeed we want to see that Q corresponds to E, then this is what we have to do. So let's consider the first case. 1. if Q corresponds to E, then it implies that Q, the value of Q in the English alphabet is 16 and that of E is 4. So if 16 is to 4, this is what you have to do. You have to subtract 16 from 4. So 4 minus 16, and this is minus 12. And since we are dealing in the English alphabet, so mode 26, and this is equal to 14. So it means that our C in this case is equal to 14. So if you are to, let's pick a sequence. For instance, let's pick KF, Q, and Q. Now we know that K corresponds to 10, F is 5, Q is 16, Q is 16, right? Okay, so if I am to add this C to the values over here, I'm going to get 24, 19, 30, 30. And 24 corresponds to the letter Y, 19 corresponds to T. Now 30 modulo 26 is 4, so you're going to get E over here, E. And YTEE is not a word in the English alphabet. So what it means is that Q doesn't correspond to E. So we have to try another alternative. So let's check this. What if instead of Q we use J? So if J corresponds to E, then it implies that we are getting 9 corresponds to 4. So if you want to find the key, we are going to get 4 minus 9, which is equal to minus 5. And minus 5 mode 26 is equal to 21, right? So using the same sequence, we have K, F, Q, and Q, right? So K is 10, F is 5, Q is 16, and Q is 16. So if I'm to add the C, which is 21, to these, I'm going to get 31, 26, 37, and 37. Now 31 modulo 26 is 5, and 5 corresponds to F. 26 mode 26 is 0, and 0 corresponds to A. 37 mode 26 is 11, and that is L. And you can see that this is a word in the English alphabet. So it means that J corresponds to E, which means that our key is 21. So now that we have 21, we can apply it to all of our cipher tests to read the message. So let's pick the first one. So we know that our first sequence is K, Q, TB, JWS, right? Okay, so now Q is 10, Q is 16, T is 19, B is 1, J is 9, W is 22, and X is 23. Now because our C is 21, we can go ahead and add 21 to these letters. So if you add 21, you are going to get 31, 37, 40, 22, sorry, another, you're going to get 30, okay, then this is going to give you 43, then this is going to give you 44. So 31 mode 26 is 5, so we're going to get F. 37 mode 26 is 11, so L. 40, 26, so we're going to get 14, which is O. 22 is W. 30 is E, so E. 43 mode 26, I'm going to get 17, so R. And 44 mode 26 is 18. So the first sequence over here is giving us flowers. So looking at the cipher test, K, Q, T, B, J, W, and X is going to give us flowers. So after knowing this, you can apply it to the rest of the cipher test, and the answer will be flowers, blossom in spring, and leaves fall from trees in autumn. So over here, so where we pick the sequence to use, the KFQQ, one could have used JQTTR. Also, you can use any of the sequence, so NS, FSI, whatever that you want, but just that after your decryption, it has to make sense. You understand? Whatever sequence of alphabet you get there. So in this case, we got 4. It makes sense in the English alphabet, right? It's a word in the English alphabet. So if you do not get a word in the English alphabet, then it means that your C, it's not correct. So you can try from C equal to 1, 0 up to 25. So in this case, instead of doing that, that's the brute force attack. So instead of doing the brute force attack, we use the frequencies of the letters. And this is the answer: flowers blossom in spring and leaves fall from trees in autumn. So that's how the Caesar cipher does work. If you like this video, please give it a thumbs up. Also share and subscribe to this channel. I'll see you in the next episode. Thank you very much. Enjoy the rest of your day. Bye.